In this section, we're going to talk about strong and weak acids, we're going to talk about strong and weak bases, and we are going to talk about acid concentration. So to begin with, we're going to talk about the fact that there are strong acids, there are also weak acids. What does that mean? What do I mean by strong acid? Well, hydrochloric acid, HCl, is an example of a strong acid. What that basically means is that if you take hydrochloric acid, dissolve it in pure water, our definition of an acid is a material that donates H+. So this is HCl is capable of donating this H+. Strong acid means that whatever your material is, it's really, really good at donating the H+. If you dissolve HCl in water, almost all of the HCl molecules will donate their H+ to the water in this case, because water is the only base that's around that's capable of accepting the H+. So if you donate HCl, if you dissolve HCl in water, because the hydrochloric acid is really, really good at donating the H+, almost all of the H pluses will be donated. If you could zoom in to a beaker of hydrochloric acid dissolved in water, maybe you could see that virtually all of the HCl's were broken apart and turned into Cl- and H3O+. In other words, there would be no or almost no connected HCl molecules like that. Because it's really good at donating the H+, you say that it is a strong acid. Now, there are weak acids as well, in addition to strong ones. This, you might remember from a previous unit, this is the formula for acetic acid. This is the main ingredient in vinegar. This red hydrogen atom is the one that is donated when you dissolve acetic acid in water. However, acetic acid is a relatively weak acid. What that means is that even though this hydrogen atom can get donated to H2O and turn it into H3O+, a lot of the times the acetic acid molecule doesn't donate the H+. You can think of it as not being that good at donating H+ to other molecules. Because it's not so good, we say that it's a weak acid. And maybe if you dissolved acetic acid in a container of water and you could zoom in and look at the molecules, some of the acetic acid molecules would have lost their H+, like this one over here. This is no longer acetic acid because it's missing its H+. But some of the acetic acid molecules would not have donated at all. They would still remain intact like this. So the idea is that there are some acids that are strong acids. They're really good at donating H+. There are other acids that are weak acids. They're not so good at donating H+. And you can see, hopefully, that with these strong acids like this, you will have a lot of ions running around in your mixture. Because of that, strong acids are also strong electrolytes, and that's a term from the previous unit. Basically, if you were to dip the fancy light bulb that we talked about in the previous unit into a container that had a strong acid, you might see the light bulb turn on very strongly. In comparison, only some of these molecules are being turned into ions. So this one is turned into an ion, but this molecule is not. Because of that, it's a weak acid. It also happens to be a weak electrolyte. So if you had identical amounts of HCl dissolved in water and identical amounts of acetic acid dissolved in water, this mixture would turn on the light bulb more strongly than this mixture, because the H pluses are disconnected almost entirely from the Cl minus. You have a lot of ions running around in this container. You have fewer ions running around in this container. So that's the difference between a strong and a weak acid. The same is true for bases. There are strong bases and weak bases, and the principle is basically the same thing. Sodium hydroxide, if you dissolve that in water, almost all of the Na plus and OH minus ions will disconnect from each other, and you will have a container that is basically almost exclusively sodium ions and hydroxide ions, in addition to the water molecules that are running around in here. But these almost entirely disconnect from each other. Because of that, you say that sodium hydroxide is a strong base. And because there are so many ions running around, you can say that it is a strong electrolyte as well. In comparison, ammonia is a weak base, relatively speaking, compared to sodium hydroxide. So if you put identical amounts of sodium hydroxide into this container with water and identical amounts of ammonia into this container with water, less of the ammonia molecules will actually accept an H plus from the water. And because of that, some of the ammonia molecules will still remain like ammonia molecules, like the one I'm circling here, but some of them will accept the H plus and they will turn some of the water molecules into OH minus. But there will be fewer OH minus molecules in this container than there are in this container. Because of that, because the ammonia is worse at accepting H pluses, you say that it's a weak base and it's also a weak electrolyte compared to strong bases like sodium hydroxide. So that's pretty much it for strong bases and weak bases. Basically, strong or weak is telling you how good the base is at accepting protons. If it's a strong base, it's really good at accepting protons or H plus ions. If it's a weak base, it's not as good at accepting protons or H plus ions. So the punchlines, not all acids are created equal. Some acids are strong, others are weak. The same is true for bases. And I don't expect you to be able to look at an acid or a base and tell which ones are weak versus which ones are strong. There are rules that are involved in sort of looking at these things and figuring out which ones are strong and weak, but you don't need to know those.